Hello everyone, welcome you all to today's lecture, and today is very important lecture design point of view. So we have to look at the design of controller using root locus. So if you remember, whenever you do design, so you have to know about design specification. So first one, the specification that we use is known as steady state error, that we calculate error of infinity equal to limit when t tends to infinity a of t, or we can use the final value theorem, that is limit when s tend to 0 s e of s. So this you already done, and detail if you do want to revise, you have to go to chapter number 7 of book by Control System Engineering by Normal S. Nice. Now the second specification that is very important, and it is related to transient response, and detail is in chapter number 6 of the same book by Control Systems Engineering by Normal S. Nice. So if you remember, I just go through the specification. We have first order system. For example, if this is the transfer function of a first order system, a divided by s plus a, we have rise time that is calculated 2.2 divided by a. Similarly, steady state time 4 divided by a, and if you remember, there was a time constant, and that is 1 over a. So this is specification related to first order system. If you remember, there was second order system, and we categorize system into either first order or second order system. So for second order system, you have omega n square s square plus 2 zeta omega n s plus omega n square. So this is the standard form of a second order system, and we define the overshoot, if you remember, exponential minus zeta pi divided by 1 minus zeta square times 100. This is only true when zeta is less than 1. So this relation is true for zeta is less than 1. If zeta is greater than 1, then we have zeta square minus 1. Okay, so but normally we are interested in zeta is less than or equal to 1. So the next one, from this overshoot, if we do some mathematical manipulation and take natural log on both sides, we can calculate zeta. That is very important, that we required. Zeta is equal to minus log of percentage of overshoot divided by 100 whole divided by under root pi square plus natural log square times percentage of overshoot divided by 100. So the third one is peak time, that is the maximum, the value of the response. That time is calculated as pi divided by omega n times 1 minus zeta square. Again, this is for zeta is less than or equal to 1. So steady state time, that can be calculated by 4 divided by zeta omega n square. Rise time, if your zeta is between 0.3 and 0.8, is calculated at 2.18 zeta plus 0.6 divided by omega n. So if we look at the S plan, how our specification look like. So this is your horizontal axis, that is represented by sigma, and this is your vertical axis, that is represented by frequency, that is j omega. This is omega n, that tells you about the rise time. As you increase omega n, means that if you go in this direction, do in that direction, your rise time will decrease in this direction. Similarly, this is the overshoot, this by the overshoot by the zeta. So as you go toward the horizontal axis, your overshoot is decreasing. Okay, but on this line the overshoot remains the same. And the third specification, that is this straight line, vertical straight line, that tells you about the steady state, that is depends upon omega zeta omega n. So if we combine all these three specification, we come up with these constraints, that our closed loop pole must be lie on this after this lines in left of plane, so that we can manage the specifications. Otherwise, if your closed loop poles lie somewhere here, you can unable to meet all the constraints or requirements of the design specification. So this is the basic idea. If you want to do it in MATLAB, you can use SGrid, that asks you about zeta and omega, and you just plug in zeta omega, that will give you this type of figure that tells you what is the area where your closed loop pole must be in. So this is the basic idea that we can use to do the design. Now we will look at what type of controllers we have, and then we look at a very simple design in today's video. And so let's start with what we have here. So look here, we have a closed loop feedback system with reference input and with some output here. Okay, so this is our controller, this is our process, this is our feedback dynamics of the sensor. So we are interested in designing this K of S. So this is our control and this is our task, and we will look at today's lecture how we can design this controller. So K of S is our controller, and sometimes people call it as a compensator that can include the dynamic of sensor as well. So the first type of controller that is used a lot is known as proportional integral controller, that is in short term called as PID, proportional integral derivative. So PID control has four different types. First one is P control, that is known as proportional controller, that is represented by capital K equal to KP. Second one is PI control, that is proportional integral control, where you have a proportional term plus an integral term in the system. If I look at the dynamics, so for this PI control, if I take the transfer function and take the denominator has S, and on the numerator we have a 0. So S is at the origin and 0 is there. So you have to move this 0 to tune this PI control. Okay, so what do you mean by tuning? Tuning means that to find out the values of KP and KI. So if you look here for this PI control, what PI control do actually, it introduce a pole at the origin. So this PI control normally used to increase the type of the system. If you remember what is the type of the system we study in chapter number 7, we say that type of the system is the number of poles at the origin. So this PI controller actually introduce a pole at the origin. So this means that it will increase the type of system. When you increase the type of the system, what happens if you have a steady state error at previous type, the next type you have a 0 error. So this means that when you use the PI control, you are looking for a constant steady state error. So if you have a constant steady state error, then you have to introduce the integral term that will reduce or zero the steady state error. So it is very important to note that PI is used to increase the system type for steady state error. Okay, now we move to third point, which is proportional and derivative control. This third type of the PID is known as PD, where we have a proportional term plus a derivative term. So this means that it will introduce a single 0 only. So you have to move this 0 so that you can meet your design specification. So design parameter is to find out KP and KD. So what this PD do actually, PD remove the energy from the system and improve transient response of the system. So PD is work as a damper. If you introduce damper to a system, is very similar to introduce a PD control. Because of proportional is introduced as a spring, so proportional and derivative this work as a spring and a damper introduced in a system. If you know that when you introduce a damper or spring in a system, it will reduce or suck out all the energy from the system. When energy is reduced from the system goes towards the stability. So that's why PD controller is used to improve the transient response of the system and make the system more stable, because it is introducing the 0. Whenever you are introducing 0 into the system, your system is more stable. Now the last term is known as PID, where we have proportional, integral, derivative, and control. So we have a proportional term, we have integral term, we have a derivative term. If we look at the overall transfer function, we have two zeros and single, again the same pole at the origin, but we have two zeros that can be placed anywhere on the real axis, on the j omega axis, anywhere. So it depends upon the tuning, how we can find these kpa kdis, and we can put this anywhere in the s-plane. Now this is PID control, and it is used a lot in the industry, and you must know that what is PID control. PID control is actually a control which has three terms: proportional, integral, and derivative. So derivative mean introducing of s, integral mean you have k by s. Okay, so the main idea is in industry, what in design control engineer do actually, for designing you just have to find the values of kp, ki, kd. If you want to find the values of ki, kp, kd, or you want to adjust these values, this is known as PID tuning. The phenomena, the technique is known as PID tuning. To find the values of kp, ki, kd, this is known as PID tuning. Now the next one is the controller type. First one is PID, next one is lead lag compensator. So again, lead lag compensator has further three possibilities. So first one is lead compensator. So word means that you are leading something. So what you are leading here, you are leading in terms of phase or in terms of angle. So this controller used to increase the phase margin of the system. So what is the phase margin, we didn't discuss, we will discuss in coming videos, but the main idea is that this controller increase the angle of the system. So the very simple formulation, we have a constant gain here, and we have a zero and a pole. So this means that this controller will put a zero and a pole, but the idea main is lead is it is only leading when zero is with the origin. So that's why it is called a lead compensator. Why? If I put a line here and I draw lines from this j omega axis to the poles and zeros, we know that the angle is positive. So that's why it is known as lead compensator. The overall angle of doing placing zero and pole is the positive, so that's why it is known as lead compensator. So the next compensator that we use is lag compensator. Sometimes we need to reduce the angle from the system, so that in that case we introduce a lag compensator. So what is lag compensator? Again a zero and pole. The only difference is that pole is near the origin, because if I put a number here, so the overall angle of this pole and zero become negative. So this is decreasing the phase margin. Sometimes we need to remove the angle from the system. So I told you why we need it, because if you remember, the root locus depends upon 180 degree angle. If your angle is more than 180 degree and we want to reach that point, if it is not following the angle condition, so root locus will not pass from that point. So in that case we use lag compensator that would reduce the angle so that we can reach that particular part of the S-plane. Because if you remember, I told you that we have specifications and we want to reach somewhere, some part of the root locus. If root locus is lying here, we are unable to reach there. So in that case we have to calculate, either we need some angle to reach here, or we need to reduce some angle to reach here. So we will use either lead compensator or lag compensator. So this is the way we have this lag compensator. Why? You remember that for root locus design we have angle inequality, so we have to meet that. So the main idea here is, if you are designing a lag controller, you have pole is near the origin, okay, or in other words, the magnitude of z is greater than magnitude of p. So last one is lag lead compensator. So where you can have network of lag and lead. So you have a look here, z plus s plus z lag S plus P lag times S plus Z lead and lag. If you combine these, this is known as lag lead compensator. The fourth one is a notch. I'm not discussing here, which has the same phenomenon. So these are the compensators we normally do have when we are going to design a controller. Okay. Now today we focus on PID, and we say that we are looking for heuristic control design. So what is control design? Tuning of a PID control. So there are these methods are quite old. That's why we call it as heuristic methods, and remain in widespread use. So the main idea is the method I am telling you, it doesn't matter what type of system you are dealing with, but they have some techniques or the methods to tune the controller or find out the values of Kp, Ki and Kd. So the main idea is that they didn't bother what type of system you are using and to calculate the controller gain. So the main idea in this technique is it is based on tuning. Similar, if you remember, you have old radios with analog radios, you just want to tune a station, you just have to move the knobs in either forward or backward, so that you can adjust the station and you listen carefully, very neatly and cleanly. So similarly here you have three knobs for Kp, Ki, Kd, and you just have to move knobs in a way that you will tune the controller or find out the controller value that will give you the better response. So before going to the tuning of PID, so we have a Kp plus Ki by S plus Kd, or we can take the Kp out, we can write it 1 plus 1 over TIS plus TDS. So here Kp is known as proportional gain, Ki is known as integral gain, Kd is known as derivative gain. This Ti is known as reset time and Td is known as rate time. Okay, so the Ti is reset time and Td is known as rate time. So Ti is equal to Kp divided by Ki. Okay, so Td is also known as derivative time, that is equal to Kd divided by Kp. Okay, now the method we are looking is known as Zeigler's Nichols oscillation method, Zeigler-Nichols curve method, Cohen-Kuhn reaction curve method. So the basic idea is that we have two types of method. One is based on oscillation and other is based on curve. So these are methods, if you want to look at the history, they will track back to 1950s. So we are looking, we are also called it in short term as ZN oscillation method, ZN curve method. Okay, so these are very important methods, and we just try to look these methods, how these methods will work, what are the rule of working of these methods that you can use in industry and use a lot, and how you can do it for a particular example. So the first method we are looking is Zeigler-Nichols ZN oscillation method. So the main idea here is that we want to find out the gain value that will make the system oscillate. So valid for open loop stable plant steps for tuning. First one, set the true plant under proportional control with a very small gain. So the main idea is that you introduce a gain controller and just give a step input to the system. Okay, so now increase the gain until the loop start oscillation. So you increase the gain and you have oscillation like this. So this is the controller. So we want to give a step input and we want to increase this Kc so that this will start oscillation like this. Now when you find this oscillation, you have to find this period and this gain. So this is the basic idea. Now increase the gain until the loop start oscillation. After that, record the controller critical gain Kp, Kc. You just find this Kc where your output start oscillation. So after that, also find the oscillation period. So this is the oscillation period, this is the gain which make this system to be oscillate. So now how to find this gain which make the system oscillate? If you remember, we can find this using the routes table, or we can use the root locus to calculate for j omega crossing. So if the gain at j omega crossing is actually give us the oscillation, if you remember. So we can also find the time period from there as well. When we find the frequency, we easily find the time period, PC as well. Okay, now the main idea is that we can use root locus to find the Kc and Kp. So this is the main task of this technique. When you find Kc, Kp, then you have do nothing, just adjust the controller or tune the controller using this table number 1. So Zn oscillation method, that table says that how you find the value of Kp, Tr, Td. So if you remember, we say that we have a controller with values Kp, Ti and Td. So you are calculating these values. How you do that? Very simple technique. For proportional control is 0.5 multiplied Kc. The Kc you find it, multiply by 0.5. Because this is only proportional control, it didn't have Tr and Td. Similarly, Pi you multiply by 0.45 with that gain and divided by the time period by 1.2. Similar for PID, you have 0.6 gain, 0.5 period and PC by 8. So this is the basic idea of finding or tuning the controller using Nichols oscillation method. Now let's look do some example. So we have an example here which is 1 over s plus cube. Find the parameter of PID or tune the PID using Zn oscillation method. So solution, how we do that? We give a step input and we want to find this Kc 1 over s cube so that it will start oscillation. How we do that? We write the characteristic equation of this, and that becomes s cube plus 3s square plus 3s plus 1 plus Kc equal to 0. Now I wrote the routes table here. It becomes 1 3 3 1 plus Kc. Now after that I just calculate the rest of the routes table. 8 minus Kc divided by 3 0 and 1 plus Kc and 0. Now if you remember, this is the case when whole row is 0, so we have to make this thing is 0 so that this row becomes 0. Now to make this equal to 0, we put Kc equal to 0. From here Kc is 8. Now we have to write the polynomial on the above, that is because this is related to s square though, so this becomes 3s square plus 1 plus Kc. So 3s square plus 1 plus Kc. Instead of Kc I put 8 here. Now I solve for s and s becomes 1 plus minus under root 3j. So from here the oscillation becomes under root 3. Okay, now this is the frequency. Okay, now from here we have 8 and under root 3. Now we will use the table and we will solve this. Tune any controller PI, PID and PID for this example. So this is the first method. The next one is known as curve methods in Nichols curve method. How we do that? The step response is approximated by a first order system. So here the main idea is to approximate the system performance with respect to the first order. If you remember, I told you that there are two types of systems, either you have first order or second order. We can approximate any system in terms of first order or second order. So here we are approximating with respect to first order system with a delay, and we say that the transfer function is k divided by 1 plus st times exponential minus sl. So this is the curve and we make a tangent to it, and from here we from where it will start, from the 0 we call it as a length L, and from this point where curve start and the tangent crosses the 1, we call it as a TP. where it reaches its maximum value, we call it TP. Similarly, the height, we call it K. Now we use these three terms to calculate the or tune the PI, and PID. So how we do that for KP, KID? For P it becomes T divided by L, Ti is infinity, T is 0. Similar for Pi is 0.8, 0.9 divided by T by L, L divided by 0.3 is for Pi. Similarly for PID 1.2, T divided by L, 2L, and 0.5 times L. So this is the way you can tune your controller. So this is very important. Just go through it again and again. I will also upload the next video with further details. So this is the first method that you can use for PID tuning. Thank you.